Okay, so let's continue from where I left off. We started talking about raster graphics and having this grid here that you can see with all the pixels. But there's another concept I'd like to introduce at the same time as we talk about pixels. And those we call, I'm going to be in the wrong color, those are subpixels. Not quite as cool as like Sub-Zero, but subpixels are something that's really important to know about. So I said above, if we scroll back up, pixels are your smallest individually accessible display elements. Okay, then subpixels are even smaller. So we have subpixels with units smaller than actual pixels. I think it's pixels. They're pixels. Actual pixels. Right, okay. So they're smaller than actual pixels. Now I'm going to talk about two kinds of subpixels. One is a virtual subpixel. I'm struggling with that subpixel word. The virtual, it's erasing. Virtual subpixel. What virtual subpixels are is just something that you do in memory, okay, yourself. So if I take this grid here, let's say I have 2 pixels by 2 pixels. If I zoom in my memory inside my program, even if my monitor doesn't support this, I envision that this is actually, whoa, that jumped. I envision this is actually, let's say, 4 by 4 pixels. So this 1 pixel here is actually 4 subpixels inside my memory. Now, why on earth would I do that? Well, the reason we do that is because it helps you to approximate more resolution than you have. Let's say that I'm drawing a black line. Now, if I do it in my subpixels, I'm drawing this nice black line shape. Okay, like that. Then what happens is, if I look at this pixel here, only one out of 4 are colored. This one here, this is 2 out of 4 are colored. This is 0 out of 4, and this one is 3 out of 4. Now I only have black and white here, but what I can do is I can approximate it by using gray, right? So when I draw this on my screen with these 4 pixels, hey, only 1 out of 4 is colored. Let's make it a little bit light. 3 out of 4, let's make that really dark. 2 out of 4, let's make it a little bit in the middle, and let's make it white. So I can convert those to shades of gray or whatever color I'm working at, and it tricks the eye. You can approximate more detail than you actually have by using subpixels. Here, I would call this a 2 by 2 subdivision, or 2 by 2 subdivision. And in fact, if you look at my website from many moons ago, I have some ray tracing pictures showing 2 by 2, 3 by 3, and 4 by 4 subdivision. And you can see how much nicer it looks as you increase the subdivisions. But I'm not going to go into that here. Now these are virtual subpixels, and they're virtual because they only exist in your program. They're completely fake. You made them up. But in addition to virtual subpixels, we also have physical. This is going to be working offline. Go away. Let's try that again. We also have physical subpixels. Now, physical subpixels are actually built into hardware. Now, typically this is in your monitor, and where the pixel itself is made up of smaller units. And some of you might be already onto this. Yeah, I've heard of this before. Typically, it's a red subpixel, a green subpixel, and a blue subpixel. Sometimes there's a white subpixel, there's 4 of them, and so on and so forth. And I'm going to come back to why it's red, green, and blue. We'll talk about that in a few more slides. But for now, let's look at what these physical subpixels look like. So I'm going to switch over to my slides. Right. So here's again the example of the virtual subpixels turning this single color green edge into this. You know, some of them would have a little overlap, so slightly green, and the more overlap, you have more green. Here is what your TV might look like, or your LCD monitor might look like. Traditional TVs, you have red, green, and blue, and this square region here, I hope you can see my pixel, my mouse pointer, I mean. This region, this is one pixel with a red, a green, and a blue subpixel. TVs often did this, and you have this offsetting for the same reasons I told you about the hex pixels. They do this to avoid jaggy lines, so it looks smoother. You add natural motion. The downside is you lose that precision. If you want a straight line, you can't make it. So LCD monitors are often a lot more uniform, red, green, blue, red, green, blue, red, green, blue, like this, so you can get that perfect precision. A PC CRT used to be, and actually it's really cool if you study cameras, the sensors do this kind of thing too. Red, green, and blue, red, green, and blue. Sometimes they put them in a non-uniform pattern, again, so you don't get that jaggy feel. It looks a little smoother. Different kinds of LCDs. This is an early LCD screen, which was really cheap to make. They had pixels like this. So you will see a lot of variation in this. I wanted to show you what I was talking about with subpixels. You can imagine this line here. This is the letter A from a font. And fonts are drawn with these formulas. And you can imagine here that this line represents the actual letter in memory. And then this is jagged type. This is no subpixels. Either it's mostly black or it's mostly white, and it goes black or white. So it's a binary. And you get these jagged edges like that. Now, if I go to standard aliasing, the method I explained in my slides, where you count roughly the proportion of, how much is my overlap, and then shade it, you'll get this nice gray edge along with the A. And that's what I was talking about before. Now, there's another, I want to do one more slide, but there's another anti-aliasing technique called subpixel rendering, where you know the layout of the subpixels on the screen, right? You go, oh, I know red's coming to the next one, and I want to bleed over a little bit, so I'll add just red to the adjacent pixel to make it feel like it fits better. It gets complicated fast. If you're curious, you can look up, and I'll put this in the notes, you can look up what's called clear type. Was a formula they use for fonts and computers, but it's really advanced, confusing, and mostly for interest. Just this idea that we can play with subpixels. We're not going to do too much of that here. Okay. I also wanted to show this. This is an example of LCD versus OLED displays. So the way that LCDs typically work is you have this liquid crystal that you could turn on and off these color filters. So you have a light in the background shining through, and you turn on the green, red, you have the green, red, and blue filters here, and you turn on and off the shutters. So you can let through the red, you can let through the green or the blue to simulate those pixels that we talked about, to give those three subpixel colors. Now the problem with these is these shutters here aren't perfect. So some light still bleeds through, and light bleeds around the corners, and light bleeds through the spaces in between the pixels here. So LCDs have gotten a lot better. I'm using LCD right now. They're just fine, but they have these problems. OLEDs work a little different. Each unit emits its own light, so it can better control the bleed around. It has an even, uniform illumination, which is difficult to do with the backlight. And also, if you want to make it black, you just turn off the pixel. Bam, the whole thing is black. Interestingly, plasma displays used to work under a similar mechanism, except plasma TVs were a lot heavier, they weren't very bright, and they used a lot of power. I have a plasma TV in my basement. It's 42 inches, 300 hertz, and they don't break. It never breaks, but it uses a lot of power, and it's like 420p or whatever, 480. It's not high resolution. All right, let's go back to my notes. Okay, so the next thing I'd like to talk about is the resolution. If I have raster graphics and a raster graphics display, like your standard monitor, then your resolution is simply the number of pixels in each direction. each dimension. Okay, so resolution, that's all that it is. So you have this big raster, and if someone says, oh, this is a 400 by 200 raster, all that they mean is typically this direction first, there's 400 dots in this direction, and there's 200 dots in that direction. That's all. So it's usually X by Y in graphics. Okay, that's nice. Unfortunately, you have to be careful. You have to be careful. In text, it's usually Y by X in text. This is stupid. I'm sorry, computer scientists can't agree. There are old-fashioned memory reasons for why that is. Nobody cares. It's frustrating. But if you're doing text, often you explain the Y first and then the X. Okay, so just be careful about that. So resolution is really important for a lot of reasons. And basically, you have some big, simple rules. If you have big pixels, it looks chunky. Okay, you can see the squares. Oops. Come on. You can see the squares. If you have small pixels, it looks smooth. Okay? You cannot see the squares. So basically, you hear people say things like, you hear people say things like, oh, more pixels are better. More pixels are better. And in fact, I'm going to show you a quick slide of common resolutions. So here's an example. Common resolutions. 1024 by 768 here. That was a standard computer monitor for ages and ages. And then we had 1280 by 1024. Then you had what they call 1080p, you might have heard of. Where is 1080p? It's 1080 lines of progressive scan. I don't know if we'll talk about progressive scan. Ask me in class if you're interested about progressive and stuff. What you have the 1080 line and then 920 this way. Then there's 2.5K, which is this blue one, and then there's 4K, which is this purple one. So you see, like what happens is if I go from a 1080p monitor, this red one here, to a 4K, because it's both dimensions that get bigger, you might think, oh, I just double 1080 to 2160, it's about double, but it's 4 times the amount of pixels. Bam, 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 bam. So because you're going in both dimensions. So every time you increase your display, you have a boatload more pixels to deal with. This actually creates a lot of problem for rendering because we need to render each one of those pixels. When you're doing 4K, that's a lot of pixels you need to think about every single frame. Okay, back to my notes. Yeah, but resolution isn't everything. More important than resolution. You don't basically, if I asked you, is this enough resolution? You don't have enough information. If that's all that you have, if I give you a picture and say, hey, is this enough resolution? You need more information to make that call. More important than resolution is how many dots per inch of display. So how tightly packed are those pixels? How many dots per inch? And what is the viewing distance? Okay. So if we come back to what I said above here, looks clunky, you can see the squares. Looks smooth, you can see the squares. That's the key point. Can you see the squares or does it look smooth? Okay. If you can see the squares, there are a few ways to fix that. Back up, because they get effectively smaller, right? Or pack in more squares per inch. So this is actually very interesting. When you buy a TV, you might want to look up these charts. For example, if I have a 50-inch TV and I buy a 4K TV and I pay extra to get all the 4K content, I need to be about 6 feet away for it to matter. Within 6 feet. If I'm further, The human eye can't see those dots. You've just wasted your money. You could deal with a less resolution. Less resolution is okay. If I have a 20-inch monitor, computer monitor, right, at 4K, well, cool. The magic distance is 2 foot 7 inches, plus or minus depending on your glasses and your perfect eye vision and so on and so forth. So if I have a 4K monitor and I'm more than 2 feet 7 inches away, I can't. It's waste. I don't need it. Okay. You don't really need it. So if you're using across a stand-up desk and you have lots of space, you might not need it. A 1080 monitor is 3 feet 11 inches. Now keep in mind, there's not exact numbers. Someone calculated them, but you get the idea. It's not about how many pixels there are. It's how many pixels per square inch at your given distance. Okay. If I'm going to put a picture on a huge display in Times Square, I might not need resolution because people are going to be, 100 feet away, right? So resolution, dots per inch and how far you are. Okay, so I'm going to stop here and take another break before we go into the next set of slides.